So, hello everyone, good afternoon. My name is Hugo Barbosa. I'm a lecturer of computer science at the University of Exeter. And today I'm introducing our seminar series in the computer science department. And it's my very pleasure to introduce Professor Sune Lehmann from the Technical University of Denmark. And so Sune is one of the leading scientists in the field of complex networks. And he is a professor of complexity and network science at the DTU, and he's professor of social data science at the Center for Social Data Science at the University of Copenhagen. And he's also the associate director of the Center for Social Data Science at the University of Copenhagen. Today, Sune is going to talk to us in his talk about modeling temporal communication networks and dynamical processes. And I'd like to ask you all in the audience to post your questions on the chat. And thank you so much, Sune, for taking your time to join us in this seminar series. And the floor is yours.
All right, thank you so much. It's a weird experience sitting here in my bedroom. I've been kicked out of my normal office by my kids. And because of the format of this, I don't see any audience except you, Hugo. So you have to kind of don't turn off your camera. Give me a little bit of life.
I'll be here.
As I present this stuff. But let me get into the slideshow. So I'm going to share my entire screen, and I've tried to how should I put this? Mute incoming messages. You know, it's great that computers connect to the internet, but I'm hoping not to get any embarrassing text messages from my mom while giving this talk. So let's hope nothing bad happens. But let's get into the talk instead. So I have a problem, or I have many problems in my life, but one of them is that I choose outrageously pretentious titles for my project. So this is actually what I called this talk when I first came up with it, but probably a more appropriate title would be something like Sune's take on higher order structures in networks. And this talk, in a way, is based on some work I did a couple of years ago, or some ideas I had then that I'm excited about, and that since then there's really been an explosion, and I'm not really up to speed on the literature. So if you're kind of super awesome at modeling higher order structures and networks, please be a little bit forgiving and just know that this comes from a place of interested in modeling networks. But before I get started, I want to say I had a great year of lots of fun publications last year. So we had some super cool work come out in Nature about mobility, which I'm also excited about, but I wanted to talk about the network stuff. So we're not going to talk about it here, but if you want to ask questions, so you have something, feel free to talk about that. And I also was involved in a lot of COVID stuff, like probably everyone. And we also had something really cool about how everyone in the world has been modeling the confidence intervals for curve ensembles wrong. So I can also talk about that. But now to the main attraction, which is a paper that's best read on arXiv. And it's mainly sort of conceptual. And that's why I really want kind of feedback, but it is published. And the reference is also here. So that's the work I'm going to talk about today. I am excited about it. I think it's a cool way of thinking about these higher order structures. So let me get into it. And as you know, in science communication, you can't just go on and on about nothing for too long in this fast-moving world. You have to cut straight to the chase, get to the point. But because I'm such a rogue and a rascal and an all-round wild man, about town or something, I'm gonna have a super long preamble to set everything up. But I promise you that I've tried to make the preamble exciting and interesting to watch. So some years ago, I purchased 1,000 smartphones. You can see the boxes here, and a postdoc, Arik, he's lying on top of the boxes, and you can see it's a lot of phones, even then. And what we did was we put custom software on all of these phones, and handed them out to all the freshmen at the university that I work at the Technical University of Denmark. With permission, we had asked both the lawyers and the ethicists and so on, and the goal was to collect information about their networks. I had this idea that if we got a really good data set, perhaps we could learn something fundamental about how people interact with each other. And so the experimental design here, I'm by no means the first person to use phones to collect data about people. This is of course happening to all of you every day by the likes of Google and Facebook and so on. But also in research, this is technology that's been pioneered by Sandy Penton's group and Nathan Eagle at MIT. But what I did that was different and made it kind of interesting and worthwhile was that I managed to convince a whole lot of these first-year university students to participate. So what had happened before is that the people had typically kind of found some people who wanted to participate, but they hadn't been densely connected. They had just kind of said, would you like a phone, a free phone? And then we'll collect all this information about you. And then, they had connected people. So that's the metaphor with the blue network, that basically you use the phone to collect data, but you don't really have a good sample. You don't have a densely connected network, so you're missing all the friendships. And it's a great measure of mobility and all kinds of things, but not so much the network. But what I wanted to do was to focus in on the network. And so what we're seeing in the blue graph is just a fake thing, like a sparsely connected random network that I generated because I was, I have to admit it, I was too lazy to get the actual data from somewhere else, but it's just to illustrate the point. But the green network is real data. And this is one day of close proximity contacts, which means that the phone measures basically who's meeting or is close to each other in the real world. So this is just one day of data from this data set. And you can really see that it is densely connected. We really managed to get a very high sampling. And if you want to see the data, I don't know how well the streaming models this, but it looks great on my screen. So Hugo, say something if it's looking terrible. But basically what you can see, I hope, is little blue dots moving around more or less smoothly. And then you can see a map underneath, and you can see some clusters. Hugo, is it running smoothly? You're muted, but
yes, it's working. It's working.
Okay, good.
Looks good.
Good, because I have some deep philosophical points I want to make about it. So what I want to say here, and the reason I show this video, is to tell people how insane and awesome this data set is. Because what you can see is that each blue dot is a person. So it's sampled every 5 minutes. So some of the movements are a little bit weird, but basically in this data set, you've often seen dots moving around like this, but when it was a simulation. But here it's really true, and I don't know if I can sort of go back in the simulation, that what we're seeing here is that each little blue dot is a person. It's a real living human being with dreams and goals and late reports and so on. And what we're displaying here is just but we also collected, information about who they're close to. That's what we're going to be analyzing now. The phone calls, the Facebook connections, and we also know about their academic performances. So we have this incredibly rich data set. This is just one channel for one day, but we have all these many data channels across almost 2 years for some of them. there's kind of a dropping off of participation, but just to say it's a pretty incredible data set. And so this is 1 day of physical proximity. And what I realized when I saw this was that this is difficult to analyze. But what happened was that we said, well, let's try and plot just what we can see for an hour. And what we found was that all of a sudden there was structure in the network coming out of this hairball. And what we realized is that when we further sliced time to be more thin, the network fell apart in this beautiful way. So if we only look at the physical proximity that occurs within 5 minutes, we see that actually the network falls apart. Instead of being a big hairball, it becomes these disconnected clumps. And so once we had done that, we could see that, yeah, of course, this is obvious. This is what you would expect, which is that what we're seeing basically is who is meeting in the real world in physical space and is away from other people, right? So by just looking at the close proximity context within a very thin time slice, the network falls apart and it falls into the groups that are meeting right then and there. Right? So I think this is incredible because almost all the time when you get more data and you collect lots of data and you have temporal data, it becomes more complicated, right? Like if you've ever modeled temporal networks, you'll know that when things change in time, you know, any measure, even clustering or something like this, all of a sudden, you know, you can disagree, or people do disagree on how to even define the simplest measures like path lengths or clustering or anything like that. But we have this beautiful case where we're adding data, we're adding what should be complexity, but actually our view of the world gets simpler. I think it's because here that basically, in a weird way, we're observing, and I'll get into this a lot more in the following, we're observing the data at the right time scale to actually see what's going on. And it's because we're aggregating over many such simple time frames that the network in the hairball looks complicated. So, of course, there's more than one time frame, but it turns out that this behaves in a kind of orderly and nice way so that we can easily match things up across multiple time frames, and sort of we call the resulting things gatherings, which basically, when you look at one meeting, will tell us, you know, when does the meeting start and how many people are in it and how the network looks and how it eventually ends again in time. And so one of my students who was doing his master's at the time did a visualization of this, which I'm showing here. And I think it's also a little movie, if I remember correctly. So time runs from top to bottom. Over on the left, you can see each gathering of people, each sort of dynamical community, if you will. The width is proportional to how many people are in the community. And the length is corresponds to how long it meets. So the view, and you can see the network over on the right. And so we call this the sausage view, which displays these kind of sausages of friendship in time. That's, of course, the hashtag for this talk, hashtag sausages of friendship. That's a terrible joke. I apologize. So yeah, so this is really what it looks like. But and I have to say, you know, when you show this to sociologists or whatever, they get excited because you can measure all these things about friendships. You know, do bigger groups of friends hang out for longer? How long do meetings take? What's the distribution? You can calculate all these interesting things. But of course, we were just thinking we're just moving ahead. So what we realized is that, well, hang on a second. If you are actually friends and not just meeting for some random reason, you're going to meet again. So we can take these sausages here and we can see, well, do they occur again over time, right? So first we match up from time frame to time frame, and next we look for gatherings over time. And we can do that because it turns out that when we look at these things, there tends to be a kind of, like I'm just showing some kind of width of how many people are in there, but there could, of course, be some kind of churn, that the people that start the meeting are not the people that are there at the end of the meeting. But when we look at for how long individuals participate, we see that there's almost always this kind of core of people that define the meeting, if you will. So the thing that we match up are not all the people that just come by and say, hey, well, how's it going, guys? And leave again. But instead, we look for where's the core. And we actually, when I say pronounced core structure, if you look in the papers and so on, there is a statistical test to say that there is actually a gap. And so we can find who is the core of people that are having this meeting, and that's what we're matching up over time. So here's a beautiful infographic showing showing what we're doing, and what's so cool about this is that what it allows us to do is to rethink how we think about the network, right? Because instead of thinking about this hairball and these hundreds of thousands of links that we have among this group of people that are just flowing through every day, instead we can think about a person as someone who is jumping from social context to social context. So we can literally think about the network as composed, instead of being composed of nodes and links, being composed of these groups, these cores. And when we think about the path through the network, here's one ego network and the cores that this person participates in that we found. And we can kind of display the path through the network in this kind of view, as you can see down at the bottom, where instead of saying, you're connecting to these and these people, you're saying, well, now the person is in this core, then they're moving over and hanging out with this group, then they're going back to this group, then they're going on to this third group, and so on. And so the object that we're describing essentially becomes much simpler. We can think about it in terms of information theory, all kinds of fun stuff. Just want to see what I have here. And I just want to make this connection that there's a beauty in this, and we explore this in much more depth in the paper. It's actually completely analogous to how we move around through space. So there was this great paper written by Laszlo Barbashi and co-authors. Xiaoming Song is the first author, where they look at the predictability of human mobility by thinking about movement through space as a movement from place to place to place to place. And of course, there's lots of repetition. And there is a direct match between panel C below and the thing in the bottom here. So you can actually analyze our movements through social space using all these methods on predictability in geographical space. So I think it's super cool. We have a lot of results on this, but remember, this is just the preamble. I haven't even started the talk yet. I'm just warming up to the talk, which is of course going to be even more fantastic than the preamble. So we wrote a paper about this. It's a nice paper, and I'm not showing off, I'm not trying to brag or anything, but we got on the cover of PNAS because we took the time and made a cool front page. And I just want to say, I make up ridiculously pretentious titles, as I said, but this one I didn't make up. This is actually someone else that wrote this thing about the principles of human social interactions. But I loved it when I saw it, I have to say. Very exciting. So when I had done this, after it was all done, I realized that this work connects deeply to work I've done in the past. So what I didn't tell you was that the whole reason for collecting all this data was I thought I had been working on something that was a hot topic in network science in the, let's say, early 2000s, namely something called community detection. And I had thought this is too much, this is too hot of a field. I've already done some work in community detection. We had done this paper with YY An and James Bagro. We'd written a paper about how to find these communities in a clever way in networks. Then I said, I'm getting out of this. I'm going to do all this data collection instead. But what I realized that when we're done is, of course, that I had been doing the same thing as I was writing about in this paper. Because in this paper, what we're basically saying is that when you find communities, you need to consider overlap. That overlap is a kind of a key part of networks, and each person is a member of multiple communities. And when that's the case, you don't get this kind of community splitting up of the network. Instead, you get big hairballs. And so we'd written a big paper about how to find these kinds of communities by clustering edges or links instead of nodes. And this is a real drawing that Jim Bagro had made back in, I don't know, 2008 or 7 or something like this. And I had forgotten all about this, but when I saw it, I was like, wait a minute, this is exactly what we did in this, much newer paper on the dynamical network. So somehow weirdly, even though I had explicitly tried to do something else, I had, of course, without knowing it, looped back around and done the same thing one more time that I had already done many years earlier. But now, of course, with more evidence behind it and so on. So it's just to, if there are any young scientists out there, whatever you're doing now, you're going to be stuck with it. It's the only thing. It's the only, at least for me, one trick person. Anyway, but it was still exciting to see that we had somehow deepened this earlier work from back in 2010. All right, this is the end of the preamble, right? So we're here. We've gotten a fancy title on the cover of PNAS. I'd collected all this data, and I'd managed to not screw it up too badly and actually write good papers about it. And I was like, this is great. And not only that, we figured out community detection. It's all about looking at these thin time slices. So I'm like, I'm ready. So the next thing I wanted to do was to say, well, let's try this method on Facebook data, right? Because I had collected both phone calls and Facebook, who was friends on Facebook and who's writing messages on Facebook. So I had lots of temporal data. So I'm like, okay, now we're going to kind of reap the benefits of this method. And so I started a master's student just because, it's a good project to try and apply this method. And he started by making some snapshots. And this is what he showed me. I'm like, wait a minute, this doesn't look like, this doesn't look beautiful and like nice communities like before. And we were kind of confused why it didn't work. And we tried to aggregate. And when we aggregated, it also looked quite different. So these are the same people, but the patterns are completely different, right? It's very tree-like. It has this more power law-y structure with high degree links. It's a completely different beast. And even worse, when we tried to find communities in this thing using the method, we found that they didn't make much sense. So what I'm showing here is a little bit more sophisticated community detection idea where we basically let information flow between the layers. So instead of doing this straightforward matching, which kind of became didn't work at all here, we said, let's just let some information flow between the layers. And so what you're saying out of the, so S is how much information comes from the nearby, the layers above it and below it. And what you're saying is that when it's very low, you can see out on the left, the communities kind of make sense, right? There's, I don't know if I can use my mouse here, but you can see, for example, in the middle over on the left, you see that there's a nice orange blob community. And if you look at the colors, you can see that the communities are kind of together on the network. But what happens when we turn up the information that we pull in from neighboring layers, we see that then the communities just stop making sense. Like the colors signify the community membership. So the more information we pull in from neighboring layers, the less sense this layer makes. So we can't actually use any information from the neighboring layers. We were like, what? This is horrible. And those beautiful sausages that I showed you earlier, when we tried to make them for this, this network, they just look horrible. There were no sausages. It was some kind of noise instead. And I just want to show you kind of as a contrast, right? So this idea that I thought was so great turns out it doesn't work at all for the Facebook data. And so now, Hugo, I'm going to call on you. So get ready. Are you there? I know probably I'm behind some windows. You maybe, but you're getting here. So I don't know if you followed the talk so far, but normally I engage the audience here because I think it's interesting. So do you have a guess? It's okay to say no.
Yes, maybe it's something related to the natural temporal resolution of the interactions you are interacting, and also like the nature of, like, one thing is like proximity based, like weak interaction, so to speak, and another something is like the stronger like interaction, like text message interactions and Facebook interactions. Would be something along these lines.
Yeah, it's related to that for sure. So when I'm on Facebook, I'm off Facebook, but if I was on Facebook, of course, I'm scrolling through a stream of stuff that's coming at me, and it's not organized by social context, right? So in space, in the real space, I'm kind of stuck with the people that are close to me. We can't just switch them out. But in virtual space, of course, I can give a like to something my mom wrote, and then immediately next I can see something that happened in my work, and I can write a little thing about that, and then I can complain about COVID to the world in general, and so on. So when you're in the stream on Facebook, you can shift topics very rapidly. So the whole meaning of kind of the temporal ordering and this continuity that we see when you meet in physical space goes out the window, right?
Oh, so all the interactions you're talking about are like all sorts of like likes and the sorts of all sorts of Facebook interactions. I see.
It's like likes and comments and so on. But it doesn't matter. But anyway, but that's one part of it. But I mean, I think that the point I want to make, and this is where we begin now connecting to this thing that's really taken off in the last couple of years, and I wish that I could connect better to this, but this is some work I did kind of before this became, but it begins to come to this higher order modeling of networks. Because what's really going on, I still think this is a nice angle on it and kind of ties it nicely together. I'm just saying I wish I had better references on the slides here because lots of people worked on this. But what's really going on is that the networks are totally different from one another on the microscopic scale, right? So if you think about it, a good example that we can easily imagine is the phone call network. And so on the left is some data on phone calls. And if you think about a very thin time slice of phone calls, it's just going to be people calling each other. That's all that can happen. So if you kind of only think about 1 second of what the phone network looks like, it's only diodes. The network disappears completely. And the only thing that's left is pairs of people that are engaged in conversation on a phone. That's it. Of course, there's some conference calls, but let's forget about those for now. They very rarely happen. So the phone network, in a way, is this thing that when you zoom in on a narrow time slice, the whole network is gone, and the network can only come as you aggregate over time. As you aggregate over time, of course, you get many phone calls, and then you begin to see the social structures. The face-to-face network we've already discussed, and of course here you see these cliques, these groups of people that are meeting, right? But on the microscopic level, in very thin time slices, they're completely different. And what the point I want to make, and I think this is so important when you analyze network data that evolves in time, is that whatever process that generates the data that you're looking at imposes really, really key constraints. So you can't get any cliques in the phone networks, excluding conference calls. You know, the face-to-face network is naturally, it's got to be fully connected cliques, because when you meet with a group, like you have to engage with the group of them. So when I realized this, I thought, is there something more general going on? And I found this nice categorization from this kind of communication studies idea. I don't think this is necessarily this is a kind of a convenient framework. It's not necessarily the truth. You can expand it and you can discuss about it. The point is not that this specific framework is correct, but it's that the idea in it more or less captures a nice way of splitting up things, but you could split them up differently. But I think that the idea is that there are categories. And so we can think about how the communication can happen as a one-to-one, where it's only dyads, as a one-to-many, that's kind of broadcast, or as a many-to-many, which is this kind of clique form. And that can happen in a way that's synchronous. So in one-to-one, it would be phone calls. You have to both be there. You have to both be active to make the call. In a one-to-many, it would be something like TV, radio, and so on. And many-to-many, here they say online chat room, but we would also say face-to-face interactions, people that are just meeting in space, chatting. And similarly, asynchronous would be something like emails, text messages, classic letters. You send it off at some time, and some other time someone reads it. Same with one-to-many, the same with many-to-many. And the cool thing, if we're moving along, is that there's, of course, a network footprint associated with this. So the synchronous one-to-one is little dyads. The one-to-many is trees. And the many-to-many is cliques, right? And again, I'll get into this. So that means that how the data comes about, how it's collected, how you design the interaction if it's online, what kind of constraints that the actual physical space puts in, if it's in the real world, matters for the types of network configurations that can even arise. You can't have cliques in the one-to-many networks. They can't form, right? And I think that it's useful to think of networks as something that comes from sequences of these things that, again, that I pretentiously called fundamental structures. And just to kind of get the nomenclature or terminology right, I want to say that I think of the dynamic class as this one-to-one synchronous, one-to-one asynchronous, one-to-many synchronous, this spot in the little matrix. And I think about the fundamental structure as the network representation of someone communicating. So let me dig into that, right? So the fundamental structure in the synchronous many-to-many would be the gathering, would be this little sausage, right? So it's the whole thing, including also the temporal span, right? So this one, we kind of know what's going on. So instead of thinking about networks as composed of nodes and links, we could think about it as sequences of these fundamental structures, these communication events. That's the idea. And of course, this aligns with a lot of new research on these higher order structures, because these are exactly higher order network structures. But here I just put them into a little bit of context. You know, so what do Facebook posts look like? You know, maybe something like this, that exactly you can connect to all kinds of people in a sequence in the stream as you're browsing through Facebook. Okay, so that's the kind of framework. And then you could kind of say, like one of my favorite real world doctors, Dr. Gregory House. So what? And I would just want to make kind of in these last couple of minutes this point that there are important consequences of this everywhere when we model and also when we compare dynamics on networks. So we already discussed community detection and how it really matters that some methods that could be great for some networks actually won't work for other networks. Another thing is like when we start counting motifs, right? So here's a paper where a group of scientists, I don't know why there's not a reference here. It's like Jure Leskovich's group from Stanford. And what they're doing is they're counting little motifs that occur in a lot of different networks. But what they don't realize is that these networks come from different dynamic classes, which means that the motifs that can even be expressed in these networks are different. Like there's constraints, there's some motifs that we shouldn't be able to see in some of them. And you can totally see this when you look at the counts, that they're very different. And it's that we can understand these differences because the motif counts are driven by these underlying structures that arise because of the way that the network is actually generated. Another thing, it's just an idea, I haven't checked, but you could also think about spreading on temporal networks, right? We have this super interesting finding that, you know, there's one stream of literature where they say, when you look at spreading on real dynamical networks, so you simulate a spreading on real dynamical data, there's one stream of literature over on the left that look at this and they find it goes slower when you do this. And then there's another stream over on the right that says, no, when you simulate it, actually it speeds up the spreading. And of course, this has to do with the type of structures, that if you're spreading on something that's a one-to-one synchronous network that only has dyads, it might take longer than if you have something that's spreading on something where we have a lot of cliques with a lot of potential in each time step for lots of infection. So my hunch is that perhaps some of these results can simply be explained by the fact that the underlying networks in some of these cases are quite different, that they have different generating processes, different fundamental structures that in turn lead to different dynamics. And here is actually one point that I found that has to do exactly like when you have social contagion and the fact that you need many neighbors active to that your chance of infection depends on the state of your neighborhood. Of course, that is highly, highly impacted by the type of network that you have. And another super important area would be null models, right? So now I'm again going to take a step back. So these are two figures from, one is from on the left is a picture Dirk Brockman has in some notes that he shared with me, which gets an overview of some of the null models you can make, and there's another one over on the right, which also is an overview of the type of null models you can make from temporal networks. So I want to take a step back here and say that when you describe temporal networks, a lot of energy often is spent on basically, how should I put it? Instead of, in the static network, we count a bunch of stuff. We count the degrees and the triangles and the degree distribution and the high order correlations. We count a ton of stuff. But because this is difficult to define in the temporal networks, a lot of times what we do is that we run some kind of dynamical process on the network, like epidemic spreading or something else. And then we have some result, but we want to compare it to something. So to kind of understand the significance of, let's say, the temporal ordering of things, we could say, well, actually now we're going to shift around the temporal ordering of when the nodes occur. So just like we can shuffle the edges in a static network, we can shuffle the temporal ordering of nodes. But we could also shuffle the edges, and we could also do some other things. So to understand the dynamical processes, we compared to these null models of the network, and then whatever thing that we're shuffling, basically we say, well, if it's the same, probably it's not that thing that made the difference in the dynamics. And if the dynamics become very different, then we say, well, probably it's the thing that we shuffled that matters. That's kind of the idea of the method of analysis. I said that a little bit quickly. I hope it was clear. Otherwise, I could come back to it. But the idea is just that there's so many ways that we can change and shuffle networks when we make these null models. And these two figures kind of create maps of all the different shufflings and reorderings and shuffling time points or shuffling, many, many different things. And the point that I would like to make is that actually, if you think about it, all of these null models, almost all of them, also wreck the whole microscopic structure of the network. So a lot of these will create time slices. So, you know, like so individual time structures of, so you take a thin time slice like let's say you take the social network that has the cliques. A lot of the shufflings are going to remove the cliques, and they're not going to be any cliques left, and so on. So by shuffling a lot of times, or randomizing, or creating null models, you're actually creating network configurations that could never happen. So there's a whole job to basically create new null models that create realistic, microscopic, thin time slices. And in the paper, there's many more examples, but this is just to give you a flavor that I think this is important. And this point that I made before on what to measure, I just thought it was interesting. I read this summary by Peter Holme, who wrote a great review on temporal networks, actually a number of them. And he says this thing, which I just copied a few moments ago, where he says that in static network theory, when we measure networks, that's the thing, right? So Barabashi and so on, they did the power laws and degree distributions, and that was what static networks were about. But for temporal networks, there's no agreement on what to measure. These ubiquitous structures are yet to be discovered. They might not even exist. And then he says, this has led the research in temporal networks down a slightly different path, where the focus is more on dynamic systems on the network and how they are affected by structure, and less on the common patterns. And so what I hope maybe can happen here, as we think about these temporal structures and in time, topological temporal, actually, maybe some of these fundamental structures can be the things that we can measure to understand network and see which networks are similar and different. And then finally, this is from a long ago version. So this point, I guess, has been made more, but I think part of the reason why I was able to realize this was exactly because I had these many different modes of communication between the same set of individuals. So this big experiment in a way paid off, that I was able to kind of make something that worked on the face-to-face network, and then realize, that it didn't work on the Facebook network. And the interesting thing, of course, is that because there is some kind of underlying social connectivity between individuals, the aggregated networks look similar, because they're all reflecting a kind of underlying social friendship structure, but that manifests differently in the telecommunications and the Facebook network and in the face-to-face network. But anyway, that's what I had. I may have gone a couple minutes over time. I hope it's okay. We had until the hour. But
perfect. Yes. Thank you so much, Sune. Fantastic topic, fantastic talk. There is actually a nice discussion going on the YouTube chat right now, and there are a couple of questions as well. Before I get to the questions, Ronaldo wants to apologize for not being on talk, because he said that he had another way less interesting meeting that he had to attend.
I know how he prioritizes. Like he just thought the other thing was way more important than being here. So I understand, and I probably no, just kidding. It's totally fine, of course.
There are a couple of questions on the. I'm gonna read them. So Marcos Oliveira is asking if there are examples of social interactions that could be statistically similar to these face-to-face, many-to-many interactions.
So, I mean, it would be nice if so are there social interactions?
I think he meant like online social interactions, maybe.
Yes, I mean the communication people had some ideas. So I mean, if we go back to this kind of taxonomy that I came up with for this, if we can find it somewhere here, I didn't make this up. This is, or I made it up and I thought I was a genius, and then I realized they had made it up many years ago. And then I had to give them credit, even though I felt it was my thing. You can kind of see it here, right? So they would say an online chat room, for example, is one. And I want to say that, you know, I think that when you get to, like a caveat I would say is that this is a nice categorization, but it's for sure it's cheating a little bit. So I think that a lot of online conversation doesn't fully fit this, right? It's asynchronous, but it's rarely kind of a clean one-to-many or many-to-many. Online, it's more like I had a previous taxonomy of this that I called some-to-many, where the idea was this thing that you kind of, as you put a post out there on Twitter or Facebook, there can be some discussion and you can close some kind of activity, but it can also be broadcast to some group. So I think that there's a lot of work to kind of work and better understand this kind of online world of asynchronous setups. I don't think it means that you should ignore it. I think it just means that this kind of rough categorization that I put up here is not necessarily the final say on the matter. I don't know if that's a.
I think it makes it's.
But at least I think it's an important point to make.
Yeah, because I think in some cases it's like, even though the data is represented as a one-to-many, the actual social interaction is one-to-one. So if someone is replying to someone on Stack Overflow, even though it's posting to a group of people, maybe that particular interaction from an individual cognitive point of view is a one-to-one interaction.
Yes. I think the key point I want to get across with this is that the engineering, the process that generates the network, puts constraints on the information flow that we don't necessarily think about. And so that when we model processes on these networks, those processes are subject to those constraints that arise because of how the system was set up. You know, like there's a limit to how we can communicate with phone calls. We have to call one person at a time. That means a lot for the dynamics. That's really the key point of this. And then it's, you know, it's dressed up in the taxonomy. And I think that there are some points that are important. But the main thing is that we really have to think about how does the data come about? What are the constraints? What are the interactions that could never happen? That I think is the key part here.
I have like many questions, but I'm going to ask some of the questions from the audience. Federico is asking. Federico Botta is asking whether or not these statistical properties would vary across different cultures, age, or social demographic groups.
Yes, I think they would. I mean, I don't know, right? Like this is, in a way, this is I mean, I can tell you the story behind the paper is that this was a kind of a grant proposal that that never got funded, and I was, and I thought I would turn it into a paper instead. So there's not a lot of analysis in here yet. This was kind of just a way to so that's also why the ideas go back quite a few years. And so there's not a lot of data. I do think that this distinction into classes gives you some idea of what can be compared, right? So I don't think it makes sense to model some dynamical process on one class, on a network from one class, model it on a network from another class, and then compare those dynamics. That you could perhaps, so the point is that if you want to compare the result of some process or something that occurs on the network, you can meaningfully compare and say, okay, we have these two one-to-one synchronous networks, and in one network it behaves like this, and in another network it behaves like this, and you can, I think they're meaningful, you can somehow compare them, but I don't think it's meaningful to compare a one-to-one to a many-to-many network. So but it would be interesting to look at differences in, let's say, many-to-many networks across cultures. And I'm sure you could find differences.
I'm reading the messages here that trying to find the where are the questions compared to like part of the discussion. But there's another question here from Evan. Evan is asking if in your work in collecting the data from the mobile phones, if you investigated the role of the buildings and the urban landscape and the physical structures around the students, if they could, like, to some extent, influence the characteristics of the interaction. He said his think in terms of space syntax.
Yeah, I think that's an interesting thought. I mean, I'm sure many kind of both spatial and also social constructs, right? So just to give an example, so in the paper that I kind of went over in the preamble, we think a lot about these structures, and it's clear that we have to distinguish between the groups that arise during the day. We're looking at a university, and we see these big groups forming, you know, coinciding with class starting, and it's clear that a lot of the social structure that we observe during the day and the coordination associated with it has to do with just people going to class, and so they're going to be sitting physically proximate, and those have totally different properties than when people meet, you know, after hours or on weekends and so on. And so there's a lot of work in that paper to kind of separate out what's happening on campus, what's schedules and structure, and what are kind of spontaneously or organized pre-planned meetings. So we definitely have to do that. And I'm sure that also spatial syntax matters there.
There's another question from the audience, more a comment.
I mean, I'm curious about the discussion. It's crazy that I can't see it. I'm like, I hope they don't hate me. But yeah, so please tell me also what's
they actually want to hear your opinion on different things here. And one of them is that Chico Camargo is asking your opinion on whether the motifs coming from these online group chats, if they are different from the motifs coming from in-person group chats, if the fact that what would be the difference from the same kind of like interaction from an online setting and a physical setting, if they would produce any difference in the motifs?
Yes. So I think this is, at least so I think that this is an interesting empirical question to explore. And I think, again, like the thing that is interesting to think about from my perspective is, again, to kind of say, so for example, if I wanted to analyze Facebook, I think that an interesting data structure to look at and to calculate statistics about would be the individual post. So instead of kind of slicing Facebook and just looking at time slices or what happened from here to here, I would say, let's look at the way in which people react to single posts and look at the temporal evolution of that and say, like, how deep do they go? How wide do they go? What's the density of the interactions on the post? And say that the post is the communication event, right? And so say, like, that to me is the meaningful thing to take out of. And if I wanted to build a simulation of Facebook, I would build then sequence of posts and responses to the posts that would match the statistical properties of Facebook. And so I think, yeah, it's not really an answer to this. My guess is that the motifs would be different, but what I'm saying is I don't think I would measure the motifs, because the motifs don't connect to what I would call kind of natural communication events. And I think it's very fruitful to think of networks to kind of say, like, the meaningful way to break it down, as I see it, is to say, like, what is a communication event, right? And on Twitter, it's a tweet. Of course, they have crazy connections and so on, but then that's something to be explored. But kind of find out what are the units of the network to be analyzed. I think that's an interesting thing or like a fruitful way to think about analyzing dynamic networks.
I have another question related to that. I'm going to piggyback on Chico's comment. because it seems that there is a behind these fundamental structures in the network, there are like fundamental process or fundamental interaction process that if you think that each the social interactions, they have a cognitive cost. So if you think like liking a post on Facebook, it has almost a zero cost. It doesn't cost time, it doesn't cost social efforts or anything like that. On the other hand, calling someone requires like a lot of like cognitive effort for someone to engage in these. Like there are a lot of like things being considered from a decision-making process before someone decides to engage in that interaction. Do you think that these fundamental structures, they could, to some extent, be linked to these inherent cognitive costs behind the social interaction themselves?
Well, yes, I think so. And I think for that reason, because I'm an old man now, I think that the synchronous motifs are easier for us to understand and connect with. So it's not a coincidence that we were able to find kind of good ways to model the face-to-face networks and the phone calls, because they're that we have good intuitions about them. And I think that the places where much more effort is needed to make progress and to understand what's going on is over in the asynchronous realm. And I think that the way that I would rephrase your question and what I would like to think about if I was going ahead with this would be to think about, what are all the new ways we can communicate when, as you say, like the cognitive effort for a link is so low, right? Like you're streaming through something, you're just attaching likes, or you're even from Facebook's perspective, they're kind of just keeping track of how long are you even, spending in your field of vision on your screen and so on, right? So the asynchronous networks, I think, are really interesting to think about from that perspective, and harder to understand.
I think we have time for one more question. I'm going to ask another question from the audience. Ronaldo is asking, what would be the ideal data out there to allow this temporal analysis across different groups, social demographics? I think it's related to, I think he's making more a comment related to, I think it was Federico's question. Do you want to add something on that?
Well, I could say that, like I wrote this as a grant proposal back in the day, and then I gave up on getting it funded. And my work package one was to kind of do a literature review and categorize the networks in the various papers and see if patterns emerged as you began to kind of group, networks that belong to the same dynamic class in the same group. And you can see, well, hold on a minute, like here we can see this type, in this grid point we can see this other type of results, so that we could begin to see something along those lines. So my answer is, I think that there's already a lot of data out there. And I think that, to me, like the first step would be to recognize that whatever process is creating the network is important. And so we begin by, finding different networks from the same class and beginning to see, are there similarities, are there differences, along the lines of all the questions that we've had so far, basically.
I think there's one, I missed one question here from the audience as well. Feihao is asking if trust between people would impact I think the structure of these face-to-face interactions that you described.
Yes. But I'm not sure how. I'd have to think about it. But for sure, I mean, we act differently, probably hang out for longer with people that we trust. If it's people we trust, the content is also different if you think about online versions. So I think all these underlying social connections also shape the network. And so the point is that there's this kind of interplay between the whatever kind of abstract relationship there is between the people in the real world, and then how it's manifested on all these networks that we record. And my point again is just that the different networks, what we see there and what can happen on them, the design or the process that generates the network just plays a big role and puts more constraints there than sometimes we think about, perhaps.
I think we are right on time. Again, I want to thank you, Sune, again for this fantastic talk. And you can see how interesting and exciting your talk was, like based on like the discussion on the YouTube chat, and it was really, really enriching and exciting. Cool. And I'm pretty sure that I read your article that you posted, I think a couple of months ago, about like these limitations of online social interactions, and like the fact that we are staring at a screen and we don't see them, we don't have feedback from the audience, and we don't have the opportunity to interact with people, especially in online conferences. But I want you to receive our virtual applause from your talk. It was really, really exciting. And thank you all for watching and for participating in the discussion. And thank you very much, Sonny.
Thanks so much. It was a pleasure. And at least I had you to talk to, and I quite enjoyed it. So it was cool. So thank you so much. And yeah, I'll hopefully see you all in person in not too long at a conference when we can go to those again. So thanks so much.
Hope so. Thank you, Sune.
Yeah, bye-bye.
Bye, everyone. Cheers.